Dear students, in the previous session we learned about what are phenols and how are they classified and what are the physical chemical properties and uses of a phenol. Today we are going to discuss about ethers, that is the last part of the 11th chapter, hydroxy compounds and ethers. The last portion we are going to learn about a new functional group that is widely used in the field of anesthetics and perfumery. Yes, we are going to talk about the class of compounds, ethers. What are ethers? Whenever we talk about ethers and their functional group, one of the Tamil movies song always ringer in my mind. Yes, in Gemini movie there is a song called as O Podu. The same thing you can adopt whenever we think of ethers. In between the R groups, you go for O, then it is classified into ethers. So these are alkyl groups, sometimes it can be aryl groups also. So in between you go for O, oxygen atom, then the class of compounds are ethers. So the ethers are derivatives of hydrocarbons. And how do we form? Maybe we can take an example of R, O, H group. And in this position, we have a OH group. Example, instead of taking an alkyl group, I go for CH3 and hydrogen. Then this is methane, CH4 is methane. So in the place of one hydrogen, if you go for OH group, then the class of compounds, we call them as hydroxy compounds or alcohols. Instead, we go for OR group, that is alkoxy group. Alkyl group, oxy group called as alkoxy group. Then we will be receiving ethers. What is the general formula? Ethers, they have CnH2n plus 2O. This is a general formula for both ethers and alcohols. So we will be elaborating about the molecular formula, and before going for the IUPAC name, let us learn about the classification of ethers. So ethers are broadly classified into two types. They are simple ethers. There is another name for simple ethers called as symmetrical ethers, and other one as mixed ethers or unsymmetrical ethers. I hope from the name itself you can derive the meaning of these two things. Terms. Simple ether means ether as a functional group as O. If you exactly look at that ether compound, the general formula, it is attached, the oxygen atom, ethereal oxygen atom is attached to the two of the alkyl groups on either side. If both the alkyl groups attached are the same, that is R and R dash are same, then we talk about simple ethers. Let me give you an example. We have a CH3O and a CH3. If you closely look at the molecule, both the sides, the groups attached are the same. Methyl group here and this side also methyl group. So the name of the compound dimethyl ether. So from the name you can understand both sides same group only. They are called as simple ethers or same ether. If you go for this molecule CH3O, CH2 and CH3, if you closely watch this molecule, one side methyl group, the other side with the ethyl group. That means one carbon atom left hand side and two carbon atoms on the right hand side. Thereby, the symmetry of the molecule is lost. So they are called as unsymmetrical ketone or mixed ketones. And both of them are having only alkyl group, R group. Then we have to call them as aliphatic ethers. In case both the sides the group attached or at least one side the group attached is aromatic in nature, then they are called as aromatic ethers. Let me give you an example. This side C6H5 and oxygen C6H5. This is a phenyl group, both the phenyl groups are attached to the oxygen atom on either side, and this is aromatic, that's why it's called as aromatic ether. And or else you can draw the structure like this, benzene ring, O, again it is attached with the benzene ring. Diphenyl ether. I am talking only about the common name, let us discuss the IUPAC name later. And here in mixed ether, I can give you one example, C6H5O, CH3. One side aromatic, that is aryl group, and other side aliphatic group, and in between connected with the oxygen atom. This is also coming under aromatic ether. At least one side it should be attached with the aromatic group like benzene ring. Then it is definitely an aromatic ether. But both the sides, the groups attached are different. That's why it is coming under mixed ether category. Here both the sides, the group attached are the same. The molecule is also symmetrical. Then it is called as a symmetrical ether or a simple ether. And if you closely look at the naming of all these compounds, in a common name, the name of the compound ends with the ether, full ether. Let us take this molecule for example. Methyl group. So on both the sides of oxygen atom, methyl groups are attached. So two methyl group. So they call that as a dimethyl ether. This is how common name goes. Both the sides phenyl group. So diphenyl ether. Here one side methyl group, one side ethyl group. So here it starts with E, this starts with M. You go for alphabetical order. So ethyl methyl ether. And if you look at this molecule, methyl phenyl ether, and this is having a special name, it's otherwise known as anisole. And I will give you one more example of aromatic ether, C6H5O, CH2, CH3. So one side ethyl group and one side phenyl group, alphabetically ethyl phenyl ether, this is having another name called as phenitol. Whenever we talk about the naming, we are talking about a common name, and there is a standardized name available, as you know, that is called as a IUPAC name, IUPAC naming. In IUPAC naming they say alkoxyalkane is then a rule for naming ether. Alkyl group, oxyalkane. In such case, how can we give a IUPAC name for this compound? Always we have to check the longest possible chain. Here only one carbon atom is available. So the name of this particular group is meth. And oxygen atom, first three letters I am going to take, oxy. Right hand side again one carbon, so it starts with meth. Since the compound ether is connected with a single bond, so it is ane. So alk, oxy, alkane, methane. So the IUPAC name is methoxymethane. It's easy to learn IUPAC. Similarly, how can you give name here? This is a phenyl group, so I take first part phen. This is oxy, so first three letters oxy. This is benzene ring, so this is phenoxybenzene. Actually, in this place, this is referred as a root word, and this is a primary suffix we learned in the basics of IUPAC name. and this meth is the group which is used as a substituent. So it is a prefix and also substituent. So that's how they give the name for ethers. And let us try naming here. So this side only one carbon atom, so the name starts with the meth, and in between oxy, and here totally two carbon atoms. I have the number from the side, so it is eth. So single bonded, the name ends with the ane. So the name of this compound is methoxyethane. Now there may be a confusion. Why not I rather start from the right side? Ethoxymethane. Can it be a name? So that shouldn't be, because we have to start with the smallest alkyl group and end with the longest hydrocarbon. So if we have to think this way, the child in the lap of the mother is the right possibility, and the mother in the lap of the child is not possible. That way always you end with the longest member. So the mother has to be the ending portion. That's why ethane. Let us try here. So one carbon here, the name of the compound starts with meth, and the group here it is oxy, and here it is benzene. So the name of the compound methoxy benzene. Similarly here, two carbon atoms, so the name of the compound starts with eth, and here the group is oxy, the functional group, and the whole compound on the left hand side is benzene. So phenitol can also be called as an IUPAC as ethoxybenzene. Similar manner we can give name for any number of compounds in ether. Let me try a little complicated one. CH3O, CH, CH3, CH2 and CH3. This is one of the compound where you can see one side it is methyl group, then this other side it is secondary butyl. So methyl secondary butyl ether, alphabetically butyl first, so secondary butyl methyl ether is the common name. How to give IUPAC name? As usual only, the one carbon atom we have to start the name with meth, and in between the functional group is oxy. Methoxy is over, and this longest possible chain here I can number from this side, so that the functional group will get least number 1, 2, 3, 4. So 4 carbon atom, it is bute, single bonded, the name has changed with the ane. So this is called as a butane. In that butane, that methoxy group, the whole group is attached to the second carbon. So how to name it? The methoxy group is attached to the second carbon, so we call it as 2-methoxybutane. So this way we can name any of the ether given. Next area we have to talk about the structure of the functional group. Yes, ethers, they have, I told you, ROR as the general formula. So in this particular ether molecule, that O is actually the functional group, the ethereal oxygen. So this oxygen's nature, if you learn only, you will understand better the structure of this molecule. So for that, let us go back. We learned in the previous chapter about, that is water's nature. And in water, there are 2 lone pairs of electron available, and that oxygen atom goes for sp3 hybridization. If it goes for sp3 hybridization, the possible shape is tetrahedral in nature. If it is a tetrahedral natured molecule, then expected bond angle is 109.5 degree. That is the expected bond angle. And the same manner, the same type of molecule only, in the place of this hydrogen, If you closely watch, ether is going to have a R group. That is the only difference. And that R group, let us take an example of a methyl group. Then the molecule of ether, oxygen atom in the middle, and it is attached with the methyl group. That means I mean to say the molecule is a CH3O CH3. This is dimethyl ether or methoxymethane. As usual story, two of the lone pairs of electrons are available over the oxygen atom. This oxygen is sp3 hybridized, and one of the bond that is connected with the carbon of the methyl group, that is with the sigma bonding, carbon oxygen sigma bond with 141 picometer as bond length. Similarly this side also 141 picometer. And here these carbon atoms are also sp3 hybridized in nature, so they show tetrahedral geometry. And in the case of water, both the sides hydrogen only, small people. And if you go for alcohol, the structure is like this: one side R group, one side hydrogen. I can just show you the nature. The alkyl group is bigger, but hydrogen is smaller. And in water, hydrogen is very smaller. And if you exactly place these lone pairs of electron over the oxygen atom, then you have two lone pairs available. These two lone pairs, they will have a repulsion. We learned there also in alcohol. Because of that, this lone pair repulsion will make lone pair and bond pair repulsion. Because of that, this bond pair will come closer. So when the bond pair, if it is coming closer from 109.5, in alcohol we experience 108.9 degree. So decrease in the bond angle between these two people experience. The same effect we expect here, but that is not possible because in alcohol only hydrogen atom on one side, but here two bigger bulkier groups are available. So they will have their own repulsion. So the bulkiness of alkyl group will repel each other, so that the molecule or the alkyl groups will try to go up. Because of that, the expected angle of tetrahedral is 109.5 degree, but what is actually existing is 111.7 degree. So this bond angle difference can also be asked in 2 mark or 3 mark, and generally the structure of ethers and why this bond angle variation, everything we have to write elaborately in line with the tetrahedral geometry and the sp3 hybridization and alkyl group repulsive effect, that bulkiness problem. Let us learn something about the preparation of ethers. And we are talking about preparation of aliphatic ethers, and in particular we are going with two types of ether, both the possibilities, that is simple ether and mixed ether, both will try to prepare. And we learned in alcohols, one of the chemical properties of alcohols, if you take the first method, CH3CH2OH, ethyl alcohol, that ethyl alcohol will react with one more molecule of ethyl alcohol in the presence of concentrated H2SO4 dehydrating agent at 413 Kelvin. By looking at the equation, you can understand very well. A molecule of water will be removed, and the side ethyl group, oxygen and ethyl group. So the formed product is diethyl ether or Hdroxy. It is a symmetrical molecule, so we have prepared a simple ether. So this is how we prepare a simple ether. And by this method, a mixed ether preparation is difficult. And if you increase the temperature to 443 Kelvin, instead of dehydration happening in the intermolecular level, this we have to understand. This type of dehydration is the intermolecular dehydration, removal of water. Instead of happening intermolecular, it will happen intramolecular, there will be alkene formation. So that is why in chemistry the reacting material, the condition is very important. The catalyst is also playing a role in predicting the speed and the nature of the product. And you may be asking, the reaction looks simple, how to learn how in the molecular level the reaction happens? We have to learn in the form of a mechanism of the chemical reaction. So mechanism learning is so simple. Let's see, look at that. We have to take a molecule of ether. There, the molecule of alcohol, where the oxygen atom is having lone pair of electron. That is treated with the concentrated sulfuric acid. Always the acids, I write the same sulfuric acid formula, HOSO3H, H2SO4 only. So that acid's capacity to give out the H plus ion, and their sulfuric acid is giving H plus ion. The alcohol's oxygen will donate a lone pair of electron. Thereby this oxygen will invite the hydrogen to go for a bonding with them. Because of that, the structure becomes a CH3, CH2O with the 2 hydrogen, and the oxygen gets a positive charge. This is the first step. And as usual, the second step, what happens is the molecule of water will be lost. Thereby this carbon is losing an electron, so it may receive a positive charge. Now that is going to react with 1 mole molecule of ethyl alcohol. So first part, number 1%, number 2% have reacted. Now number 3% has to go and react. So the second alcohol is nothing but, I can write this way. It is going to react with the alcohol molecule CH2 and the CH3. As usual, alcohol oxygen is having 2 lone pairs of electron. Out of that, 1 lone pair is donated for this alkyl group, is positively charged. Then there will be a new bond formation, that is CH3, CH2O, and this hydrogen, since oxygen has donated lone pair, it receives positive charge. Again CH2, CH3. It looks like a lot of arrow marks, positive, negative charges, but the mechanism is always it is similar in nature only. And once this is over, we are adding a molecule of water, H2O. H2O, I can write HOH. So this oxygen is again having lone pair of electron. It is going and forming a bond with this hydrogen. So hydrogen is coming without electron, so it will come out as a H plus. So the H plus and the H2O join together to form H3O plus, that is hydronium ion, as one of the product. Now this pair of electron goes over oxygen atom to neutralize the positive charge. The resulting compound is our product on the right hand side. That is CH3, CH2O, CH2 and CH3. So in one step we do a reaction by reacting 2 of the reactants and removing water and sulfuric acid. But in molecular level, this is how the total product formation will happen. Step by step manner. And now the molecular level, the influence of the catalyst also important, or the dehydrating agent. And if you are going for the next method, we can prepare alcohols by a very famous method, Williamson's ether synthesis. So in this method, usual reactant is going to be sodium alkoxide and alkyl halide. These 2 things will react. Let us take an example. Here this method is only applicable for simple ethers preparation, and here you can try simple mixed, both are possible. And here if you get a mixed ether by means, the separation is difficult, but this method you can do it. And sodium alkoxide, I am going to take an example, CH3 CH2ONA, and that is going to be reacting with methyl iodide. This way I am taking for the purpose of removal. As usual, NaI is removed and the resulting product is CH3 CH2O CH3. See here simple ether, here we have formed a mixed ether. So this reaction will follow SN2 type of mechanism, substitution nucleophile. So the substitution is happening. So the substitution nucleophile is involved. So substitution nucleophile bimolecular when we talk about primary alkyl or halides. The alkyl halide taken as primary nature goes for SN2 type of mechanism. And suppose the alkyl halide, alkoxide taken as tertiary in nature, and you go for primary alkyl halide, primary RX, then you will get a mixed ether. Instead, you go for primary alkoxide and tertiary alkyl halide, then you will get a double bonded compound called as alkene. So the choice of the alkoxide and alkyl halide is important for the preparation of the required ether. So that is why Williamson's method is important. And in the third method, we are going to talk about diazomethane's influence. That is, we are talking about a process called as a methylation process, addition of a methyl group. How do we do it? In simplest method possible, you can take diazomethane CH2N2. Nitrogen is otherwise known as azo. So 2 nitrogen we call as diazo, and this is methane. That is going to be treated with the simplest alcohol. Maybe I can take a methyl alcohol. So this CH2 group is going to join with this hydrogen. Methylation takes place. And this particular reaction will give you a product CH3O and CH3. So formation of a dimethyl ether. It's an example for a simple ether, and otherwise IUPAC is the name methoxymethane. So this is how we prepare the ethers. And here the requirement of HBF4, that is fluoroboric acid presence, is required for this particular reaction. So these are the methods of preparing ethers. And when we are talking about ethers, we have to learn also about their physical properties. So as you know very well, ether is looking like a replica of water molecule, and it has oxygen on either side. Instead of hydrogen, we are attaching with the R group, and it is also showing the polar nature. For example, if we go for ethyl group on both the sides, CH3, CH2, CH2, CH3, that is, it shows 1.18 as a dipole momentum. So that is vector sum of both the sides, alkyl group, they go for calculation. And since the oxygen atom carries a lone pair of electrons and is a little electronegative in nature, responsible for the polar nature of the bond, it can also goes for intermolecular hydrogen bonding with the neighboring water molecule. So because of that, the solubility of lower members of ether, and ether acting like a solvent both for a polar and non-polar molecule is explained by this high boiling point and solubility with the intermolecular hydrogen bond. Let us learn now the chemical properties of ethers. How do ethers react chemically? So this chemical properties, let us divide into two portions. First portion we talk about the aliphatic type of ethers. The next one we will be talking about aromatic, where we also talk about the electrophilic substitution reactions. And chemical properties of ethers are little less compared to alcohols. As you know, both the sides ether molecule is having an alkyl group which is bulkier in nature, so the reactivity is a little less. Even then they go for reactivity. The first one, how do they react with the HI or HBr, that is a hydrobromic acid or hydroiodic acid. So when we go for such reactivity, let us take a simple ether CH3O CH3, methoxy, methane or dimethyl ether. Then addition of HI makes a very simple removal, left side hydrogen, right side iodine, you will get one of the product as methyl iodide, other side methyl alcohol. This is very normal. But when there is a difference, you have a mixed ether, that is CH3O, CH2, CH3. In this case, if you are adding HI, now we have a confusion whether to add a hydrogen left side, iodine right side, or iodine left side, hydrogen right side. Let me give you this. Always iodine goes to the left side and hydrogen goes to the right side. In such a molecule, why? The reason is left hand side you can see an alkyl group where only one carbon atom, right hand side an alkyl group with the two carbon atom. So always the iodide will prefer the lesser number of carbon atom having alkyl group, and hydrogen will go to the other side. Thereby you can expect the product one side methyl iodide, other side ethyl alcohol. This is one of the product. So this can be explained only when you understand the mechanism of the reaction. How do this mechanism goes? The same story only. We take CH3O, CH2 and CH3. The molecule I have taken. That I am going to treat with a HI. When you react with an acid, as usual story only, the bond breaks heterolytically, H plus and I minus will be receiving. Since the previous method also we learnt, the oxygen carries lone pair of electron. That will be donated and protonation takes place. Then the next step, CH3O, one hydrogen, oxygen is a loser of electron, will get positive charge, and here CH2 and CH3. This molecule, the bond between oxygen and hydrogen is actually, because of this hydrogen linkage, oxygen is getting a positive charge. So the bond between oxygen and hydrogen becomes stronger. The bond between carbon and oxygen becomes weaker, so that this bond shifts here, making the positive charge neutral. So now the loser is carbon, he will get a positive charge and this molecule will come out as the ethyl alcohol, CH3, CH2OH. And outside iodide is waiting, that will join with the CH3 to form the product as a CH3 methyl iodide. As one of the product, ethyl alcohol is another product. Imagine only one molecule of HI is added. Now I am trying to add two molecules of HI with the same molecule. That is ethyl methyl ether. So I am breaking the bond and adding one hydrogen and iodide. See, there again breaking the bond, adding an HI, and a molecule of water will get removed, and both the sides iodides will be formed. Here the side methyl iodide and this side ethyl iodide. So excess of HI or HBr will convert them into alkyl halide. So this is what we are learning it as how do they react with the HI. Then the next reaction we have to learn about for auto-oxidation. And when this reaction is being tried in the laboratory, the people who are in the laboratory may not be safe, because this particular ethers should never be heated to dryness. Sometimes carelessly if they are heated from the atmosphere, it will gain the oxygen and it will go for a formation of a peroxide. Peroxides are highly explosive in nature. So this reaction should not be tried. So what is actually happening with the ethers? When we take a molecule of ether, CH3, CH2O, CH2, CH3. This is a diethyl ether. That ether as usual carries lone pair of electron. It joins to the atmospheric oxygen. There are two types of products possible. One is CH3, CH2O and O, CH2, CH3. See, this is how they form peroxide, diethyl peroxide. So the bond between oxygen and oxygen is very weak, so it will break very fast and it will lead to explosion. And sometimes what happens is the other product is also possible. CH3, CH2O, CHOOH, hydroperoxide formation is also possible. So if you closely look at the molecule, at the first position, Hdroxy hydroperoxide, ethyl hydroperoxide is the product. 1-ethoxy ethyl hydroperoxide will be the product. So these are all unstable molecules. So we should understand heating ethers is not safe. And what are the other chemical behaviors of ethers? Other chemical properties. As usual properties only, let us take ether molecule in the middle so that learning becomes easier. CH3, CH2, CH2, CH3. I have taken diethyl ether. In some of the reactions, we are adding PCl3 or PCl5, they are all chlorinating agents. When you do that, the bond breaks this way, and one chlorine here, PCl3 here, and chlorine here. You can have a easy guess when any of the ether is treated with PCl5 phosphorus pentachloride, 2 molecules of ethyl chloride and one POCl3 will be a product. So 2 molecules of ethyl chloride and phosphorus oxychloride is another product. In case I am going to treat this molecule with dilute sulfuric acid, dilute sulfuric acid will supply more water. So that hydrolysis reaction, that is dilute H2SO4, that means it is supplying more amount of water. So the bond breaks here and a molecule of water is being added. If you closely look at this, CH3, CH2OH ethyl alcohol, CH3, CH2OH again ethyl alcohol. So there will be formation of 2 molecules of the ethyl alcohol. This is another type of reaction. In case the same molecule, we are going for acetyl chloride, CH3COCl. In the presence of anhydrous aluminum chloride or zinc chloride, and this diethyl ether, the molecule I can write this way. One side CH3CO group is added, other side is Cl is added. You can break it this way. So right hand side there is a formation of ethyl alcohol, ethyl chloride, CH3, CH2, Cl. Left hand side you can see CH3, CH2, COOCH3. So this is nothing but ester. So formation of ester also can be possible, and the name of the ester is ethyl acetate is the name of the ester. So we have prepared ethyl chloride, we have prepared ethyl alcohol, we have prepared even ester from diethyl ether. Suppose if you are treating the diethyl with ether with more amount of chlorine in the presence of sunlight, then the alpha beta position hydrogens available will get substituted. You will get the product CCl3, CCl2, O, CCl2, CCl3. That means all the chlorines are removed, all the hydrogens are removed and chlorines are added. So it is called as a perchloro diethyl ether. Perchloro, both sides ethyl group, so diethyl ether. So these are the probable chemical behaviors of aliphatic ethers. Dear students, till now we were talking about the chemical behavior of aliphatic ethers. There we were not worried about the electrophilic substitution type of reactions. Only we were worried about nucleophilic substitution. But now when we talk about aromatic ether, the simplest ether, let us take a benzene ring with OCH3. This is called as anisole. It is called as a methylphenyl ether or methoxybenzene. This is nothing but anisole. So whenever we are talking about anisole's chemical behavior, it has also benzene ring, and benzene ring can invite electrophiles. What are electrophiles? Like bromonium ion or nitronium ion or CH3CO plus group. This is acetyl cation. All these groups are electrophiles, electron lovers. And benzene ring is a place we have alternative double bonds available. So the benzene ring will invite. There the presence of methoxy group in the benzene ring will direct only to ortho position or to para position. It is actually an activating group. It will make the benzene ring to bring more amount of electrophiles, electrophilic substitution reactions. So similar type of reaction is possible at ortho and para position. Suppose let us take example of bromination, that is halogenation they say. Halogenation can be addition of halogens like chlorine, bromine, iodine and all. And in this case, if you take methoxybenzene, that is anisole, and you are treating with bromine water, and in the presence of ethanoic acid or acetic acid presence. And as just now I told you, there will be hydrogens available in every place of benzene ring, every corner of benzene ring. And we are worried about only this ortho hydrogen and para hydrogen. And if you go for bromine addition, HBr will be removed, bromine gets attached. And we'll get one of the product at a para position brominated, and the name of this compound is para-bromoanisole. And this doesn't even require the presence of acetic acid. Even without the catalyst, this reaction is possible because the para isomer is the major product, and along with that there is another minor product is also possible, that is anisole. In the para position, one of the bromine added. So in the ortho position, one of the bromine added. So the product name is orthobromoanisole. So this is the major product, this is a minor product. Name of the reaction is halogenation, and we can go for a nitration process. So in nitration we have to talk about a nitrating mixture, that is the concentrated HNO3 nitric acid and the concentrated sulfuric acid H2SO4. So the nature of this particular mixture is to give a NO2 plus ion. As usual reaction only, the benzene ring and OCH3, this is called as anisole. Anisole will activate at ortho position or at para position. As usual, I am taking the hydrogen available in those two positions. We are adding sulfuric acid and nitric acid. Nitric acid formula is a HONO2. A molecule of water will be removed and that will be taken by sulfuric acid. So NO2 group added at ortho or para position. So both the products are possible. In halogenation we saw the similar nature only. The most probable product is in para-nitroanisole, and the minor product is also possible, that is ortho-nitroanisole. This is ortho-isomer, this is a para-isomer. So this particular type of reaction is a nitration reaction, and the next one we are going with alkylation. And for alkylation or acylation we need the presence of anhydrous aluminum chloride AlCl3, and in the presence of carbon disulfide this reaction will take place. If you take anisole, that anisole's ortho positions hydrogen and para positions hydrogen will be our target. I am going to add CH3Cl, then HCl will be removed and a methyl group gets added here. Then the products are one possibility, methyl group and para position a CH3 group addition, or else you go for in ortho position the electrophilic substitution reaction takes place. Then the product will be OCH3 and CH3. So this is a 2-methoxytoluene and this is a 4-position methoxy group. So 4-methoxytoluene. So these are the two possible products. In all these reactions you see the learning of chemistry is easy, because only what we are doing, we are removing one of the hydrogen and adding a bromine or NO2 group or a methyl group or CH3CO group. That's what is happening. All of them happens only at ortho or para position. That too, the most probable isomer is a para isomer only. Major product will be para isomer. The last area of our topic is about uses. So uses of aliphatic ethers. For example, we go for the CH3, CH2O, CH2 and CH3. Diethyl ether. See, diethyl ether is a wonderful anesthetic. We learned in chemistry in everyday life. Anesthetics are the reagents that will make a patient unconscious before doing the surgery. So they will give diethyl ether. It is a volatile substance which will go and make the central nervous system inactive, and the surgery will be done. Afterwards, reversibly the consciousness will come back. So very good anesthetics. And these ethers are, we learned in physical properties, they are very good solvents because of the capacity to go for intermolecular hydrogen bonding. They can be used for extracting the organic compounds from the plants, herbs or important materials out of an organic mixture. And the solvent job is to dissolve and bring it out, and after a few seconds you leave it outside, the solvent alone will evaporate. Then the recrystallization of the product is possible. So this is one of the advantages. It's used widely as a solvent. And best use of this ethers is in the automobile or vehicle engines, like gasoline, diesel engines, as a starting material, like it will be a volatile substance. So immediately the initiation is possible. So the ignition, by giving a spark, the vehicle will start. Our next use of diethyl ether is in the field of refrigerants. What are refrigerants? We have learnt all these ethers are volatile materials and they easily from liquid state by gaining the heat energy will go to the vapor state. Since they are removing the heat energy from the atmosphere or the area or maybe a refrigerator inside, the inner part or the air inside will get cooled. So the refrigeration, instead of going for CFCs, which are very dangerous for the ozone layer, there is cause for depletion of ozone layer, we can go for safest refrigerants like diethyl ether. And we have to learn in the next part the uses of C6H5OCH3. This is nothing but anisole. And anisole we learned is an example for a aromatic compound. From the classification we can understand aroma, sweet smelling. So most of these anisoles are used as perfume making, that is in the perfumery it is mostly used, and also their nature is to create the pheromones, that is used as an insecticide. It will invite the insects by sending the smelling compound, thereby they will kill them. And in all these areas the ethers are used, but sometimes when we use a perfume bottle and we spray them in front of the burning flame or we heat the container of the perfume bottle, all of these are unsafe practices. The reason is these are all volatile compounds and inflammable too. Easily they will catch fire and burn. When the volatile liquids you heat the outer core or the vessel, the heat energy will immediately convert them into liquid state and the pressure will get mounted, they may explode. They are not safe. And similarly, they are also used in pharma companies and pharmaceutical preparations. These ethers like anisoles are used, and ethers, since their behavior is easily evaporable, they can be very well used as a fragrance giving material in many of the industries. So now you would have understood the importance of alcohols, the different types of alcohol, phenol, ether. They are all used by us in everyday life, knowingly or unknowingly, and it's good that we learn their physical behavior, chemical behavior, and also their uses. Now what is important, dear students, in all the organic topics, the best way to grab these content very easily is understand the concept 2 or 3 times, try to have writing practice. That will make you to go for perfection and you won't forget that particular answer for a very long time. Before exam also, the revision of organic lessons are very easy by looking at the title of the equation or reaction, and in just you can write a small hints about them, the condition, the catalyst and the product, and if you know the names of the basics of IUPAC names and all, organic chemistry is the simplest area. I hope this hydroxy compounds and ethers you will start preparing question by question and concept by concept and try to get ready for the test. Thank you.